Previously, we have learned that to form an optimal classifier, we need to look at the conditional probability of y given x. So a natural approach would be to collect some data and then estimate the joint distribution of x and y, and then compute this conditional probability of y given x. In particular, we're going to learn the joint by factorizing the joint as the marginal of y and the conditional of x given y. And the marginal of y is relatively easy to estimate because y is a discrete random variable. So we basically estimate the marginal frequency of each class. And then we estimate the distribution of this feature vector of x given within each class. Once we learn those two, we can get a joint and then compute the conditional. Such a framework where we learn a classification through this path, often referred to as a discriminant analysis. In particular, we're going to talk about three classification rules under this discriminant analysis umbrella. One is quadratic discriminant analysis, linear discriminant analysis, and naive Bayes. And we'll also talk about the connection between LDA and FDA. First, let's refresh our memory on how we derive the optimal classifier based on the Bayes theorem. The key quantity we wanted to compute is the posterior probability of y equal to k, given we observe a feature vector little x. Now, by definition, this conditional probability is equal to the joint divided by the marginal. And then for the numerator, which is a joint distribution of x and y, we further factorized as the marginal of y times the conditional of x given y. And now you can see that I keep the denominator x, the marginal of x, the same. Because you're going to find out when we evaluate this conditional probability, we wanted to find out which k value will maximize this conditional. And that k has nothing to do with the denominator. So this is why you're going to find out we don't even need to evaluate the denominator and the marginal of x. Now let's use pi k to denote the marginal of y. And then use f sub k to denote the class-specific distribution for x, which is this one. Then as I just said before, we aim to find out which k will maximize the conditional. So that's equivalent to find k which maximizes the numerator because the denominator doesn't depend on k. So this is just a recap of what we just described. We wanted to, when we try to find the optimal prediction for little x, the feature, we basically wanted to find a class k that maximizes the product of pi k times fkx. And the pi k is the marginal probability of y, and basically the marginal frequency for the k's class. And f sub k is a conditional density function for x. And when we try to maximize the product, the k that maximizes the product, that would be the same k if we take a log transformation of the product. So we just need to evaluate log pi k plus log f sub k for each k value, and then find out which k maximize this sum of logs. So you can see, to construct an optimal classifier, all we need to do is to estimate the marginal frequency of y and the class-specific distribution for x.